Hello everybody, and welcome to 4-1, where we talk about inverse variation and the reciprocal function. Now, the first thing we're going to discuss is the difference between direct versus inverse variation. Now, direct variation is something you've actually dealt with before, but you didn't know it by the name direct variation. So if we look at the equation for direct variation, or if we look at the relationship between x and y during direct variation, essentially what's happening is y is going to equal some value multiplied by our x. And if you look at what this looks a lot like y equals mx plus b, just without the b. And if you look at a chart, right, let's say that k in this case is 16, so it's being scaled by a factor of 16. If we plug this in, well, this just looks like a line with a slope of 16, right? And if we look at the chart over here, we'll notice that as x keeps increasing, so here we have x is 1, x is 2, 3, 4, and 5, you'll notice that y, if we plugged it in here, if x is 1, then 1 times 16 is 16, so y would equal 16. And you'll notice that that's actually going to continue happening. So if we have x is 2, 2 times 16 is 32. When x is 3, y is 48. When x is 4, y is 64, and so on. Now, if we look at this, we'll notice that as x is increasing, y is also increasing. Now, if you want to be able to try to find the scale factor based on our x's and y's, well, what would you do before to find the slope? You would do rise over run, which is y over x, and you'll notice we're going to get a constant slope, and that's what's actually going to make this a line. And that makes sense. So if we go to Desmos real quick, drop over here to our best friend, if I turn on, just toggle this on, y equals 16x, which is what we're looking at here, is this line. And you'll notice that it goes up pretty quickly, and that's because our slope is 16. It's rising 16 for every one that it's going over. So that's all direct variation is. Direct variation is literally just a line, and it's the relationship between our x and y values. Now, inverse variation is a little bit different. So, inverse variation, right, also known as indirect variation, is when our y and x values are inversely proportional. Now, what this means is that as x gets larger and larger and larger, y is actually going to have to get smaller and smaller and smaller. And it's represented by this equation here. So it's actually y equals k over x. And let's just go ahead and take a look at the chart, and we'll be able to plug this in. So let's use the same scale factor. Let's plug in a 16 for k. Okay, if we plug in a 16 for k, and we just go up by the factors of 16 for x, so let's start at 1, right? If x is 1, well, then we have 16 over 1, so y is 16. So you'll notice when x is 1, y is 16. That all makes sense. If we plug in a 2 for x, well, 16 divided by 2 is 8. So you'll notice that we have 2 and 8. And if we keep following this pattern, if x is 4, then y is 4, right? If x is 8, y would be 2. And if x is 16, 16 over 16 is just 1, so we have 1. So you'll notice that in inverse variation, what happens is as our x actually gets bigger, our y value is going to keep getting smaller. And it's not only that it's getting bigger and smaller, they're getting bigger and smaller directly inversely proportional to each other. So you'll notice that if we multiply the x and the y values all the way down here, that the x and the y values multiply together to get our common scale factor here, which is k. So that's the difference between direct and inverse variation. Okay, direct variation is as x increases, y increases at the same scale. Inverse variation is as x increases, y decreases at that similar scale. So in one, you can take y over x to get this, and for this one, you're going to actually multiply our x and y's to find the scale factor that's the same. All right, so let's look at a couple of problems. That's something we could run into. Just main takeaway, direct is as x gets bigger, y gets bigger, and inverse is as x gets bigger, y gets smaller. So it's actually the opposite. Okay, so let's look at a couple things here. Is the following chart direct variation, inverse variation, or neither? Well, there's two things that are important in order for it to be direct or indirect variation. One of it is going to have to be that as x increases, y increases, or as x increases, y decreases, as we've said. But you'll notice the other factor that's important in order to make these an actual direct or inverse variation is that the scale factor has to be the same across the board. So the first thing we have to do is determine if we're talking about direct or inverse variation. And then after we figure that out, we have to determine if the scale factor is actually the same across the board. So let's go ahead and take a look at this. So as we look at our chart here, we'll notice that if we go from 1 to 12, right, let's look at this first, right? As x is increasing, right, we're going from 1 to 2, 2 to 3, 3 to 4, 4 to 6. So x keeps getting bigger, right? As x keeps getting bigger, y is going from 12 to 9 to 6 to 3 to 2. So y is getting smaller. So it's definitely not direct variation, because if it was direct variation, this number would be getting bigger as this number would be getting bigger, right? So it has to be inverse variation. So let's see if it is inverse variation. And the way we're going to do that is just like we did up here, right? If we look up here, we multiply the x by the y, and we just see if we get the same number all the way down. So let's try it for this. So here I've got 1 times 12, which is 12. Right? I have 2 times 9, which is 18. Yeah, these numbers aren't the same. 3 times 6 is 18. Okay, that's kind of consistent, I guess. 4 times 3 is 12. It's just kind of jumping around. 6 times 2 is 12. So it's definitely more of an inverse variation pattern, but we cannot say that it's inverse variation because our scale factor is not the same, right? So in this case, the answer would just simply be neither, right? This is neither kind of variation. All right, so let's go ahead and jump down to one more kind of question. And this one's a little bit more challenging. Let's give it a shot. So write an equation to represent an inverse function where x equals 10 when y equals 3. What is y when x equals negative 6? Well, the first thing they told us is that this is an inverse function. And we know that for our inverse function, we're going to have y equals our scale factor over x. Okay, and what did they tell us? Well, they told us that in this inverse function, it looks like we're x equals 10, y equals 3. So let's just plug it in. So we have y equals 3, so 3 equals k over 10, right? And now to get k by itself, right, in order to find the inverse function, we're going to need to know what k is, right? So let's go and figure this out. So we'll multiply both sides by 10, right? So we'll multiply this side by 10, which means we multiply this side by 10, and we're going to get 30 equals k, which means that our equation for this inverse function is just simply y equals 30 over x. And this is the equation, right? And actually what's interesting is, do you see how we multiplied this 10 by 3 over here? So like over here, we multiplied 10 by 3. If we actually go back up to what we did up here, remember that this is nothing more than the x and the y values being multiplied together. And that's what our k is going to equal, right? Our k is just our x times our y. And if we come back down here, well, our x was our 10, our y was our 3, and our k ended up being 30. Okay, so far so good. But what's the second half of this question? It says, what is y when x equals negative 6? Well, we have our function right here, right? So if that's our function, well, what is y when x equals negative 6? Let's figure it out. Y is what? Well, it's 30 over x we said is negative 6. Okay, well, what's 30 divided by negative 6? So y equals negative 5. So when x is negative 6, y equals negative 5. And let's think about this, right? If x is negative 6 and y is negative 5, negative 6 times negative 5 equals 30, which gives us the same scale factor as we had up there. So everything checks out, right? So write an equation to represent an inverse function where x equals 10 when y equals 3. Well, we know that our inverse function is y equals k over x. So what we're going to do is we're going to just kind of plug in the information they gave us, solve for k, and then we can write our function. And then once we have that, we can solve the second part. What is y when x equals negative 6? Well, y equals 30, right, over negative 6, because they gave that to us. And we solve, and we get that y has to equal negative 5. All right. And essentially, that's it for inverse variation and directed variation. All right. So now let's look at what is the reciprocal function. Now, the reciprocal function is something that we haven't really looked at before, but it kind of ties into this inverse variation that we were talking about before. So let's go ahead and jump over to Desmos for a second. So on Desmos, now what I'm going to do is I'm just going to input. So right now we have the y equals 16x, right? Well, what happens if we take that exact same function, but we take the inverse variation version of it? So in other words, if we take the y equals 16 over x, right? Remember how we had y equals k over x? Well, in this case, we're saying k is 16. What happens if I toggle that on? Let's see what it looks like. All right, so that's a little interesting, right? And I went ahead and I made this chart for you just so you can see. You'll notice that if we start at 0 for x, x is undefined at 0. Well, that makes sense because if we look at our function, if x is 0, the graph is 0 is undefined where x equals 0, right? It can't equal 0 because it's in the denominator, which means that we cannot have any x value that ever equals 0. So what you'll notice is that these lines here, right, as they get closer and closer to 0, it's going to keep getting close, and it'll get infinitely close, but it'll never touch it because it can't, right? And then what's interesting is you'll notice that because it's an inverse function, as y gets huge, x gets really small, right? X gets closer and closer to 0. And then the opposite's true. So as x gets really huge, y is going to get closer and closer to 0. So let's do this, right? As x gets smaller and smaller and smaller, right? X is really, really, really close to 0, right? X is just, it's getting smaller. Well, what's y doing when x gets smaller? Y is just shooting up, right? Y is getting bigger and bigger, right? Because it's an inverse function. So as x gets smaller, y gets bigger. And it's the opposite is also true, right? Let's just look at this top quadrant here. What happens when x gets really, really, really big? Well, let's look. As x gets really, really big, right? We're here getting into the 80s, 90s. X is getting huge, right? What's y doing? Y is getting closer and closer to 0, right? So this is actually exactly what it should be, right? As our x's are getting bigger, our y's are getting smaller, and then as our x's are getting smaller and smaller and smaller, y is getting huge, right? And then of course it'll never touch 0 because it can't. Okay, so this is essentially what this looks like. This part up here is actually just all the positive values, and then the one down here is just what happens if it's negative values as well, right? So that's why it kind of flips on the graph. Okay, awesome. So let's think about a couple concepts here. Okay, well, what is the reciprocal function? Well, the function is just y equals 1 over x. Now, 1 can be any number. This is actually our k over x, right? But in this case, we're just going to use for 1 because this is the parent function of this, right? Y equals 1 over x is the parent function. So let's talk about a few concepts. So the domain, okay? If we go back to our function here, the domain is the set of all x values, right? Well, where is x? X can literally be anything. If I start all the way up here, right? Or if I start all the way negative, you'll notice that we're good. X is good, x is good, x is good. Oh, wait. What can't x equal? X can't equal 0, right? So x can literally be anything except for 0. And in fact, when we write the domain for our function, we're going to say that the domain is x such that x cannot equal 0. And this is how this is written, right? It's in brackets. This means x such that x does not equal 0. And then if we look at our range of our function, it's going to be very similar, right? The range, well, what does y never touch? It never touches this y-axis, right? Because it has to be inversely proportional. So if it can't touch the x-axis, it can't touch the y-axis either, right? So if it can't touch the y-axis, but it can touch everything else, like I said, our range is going to be almost identical. It's y such that y does not equal 0. So basically our domain and range can be almost a set of all real numbers. The only thing it can't be is the zeros. Now, what's really cool is if we go back to this line here, or go back to this thing, imagine if I created the line, and I'll just create these over here real quick. If I create the line y equals 0, and I create the line x equals 0, and I'm going to see if I can make both of these red. There we go. You'll notice that our red lines here are actually lines that the purple function here will keep getting closer and closer to, no matter where we go, right? The purple is going to keep getting closer and closer, but never touch the red, right? Well, what these red lines are is there a concept known as asymptotes. And asymptotes are lines that we can draw to kind of guide us, to show us where our lines are never going to, or where our graph is never going to cross. So if we go back here, right, an asymptote is a line which the graph approaches, right? But you'll notice that the graph approaches it, but it never ever crosses it. So in this case, we have two asymptotes. We have the asymptote x equals 0, and we have the asymptote y equals 0. And if you want to draw a graph, usually it's a good idea to start with the asymptotes and then kind of draw towards it. So in this case, I've made the dotted asymptotes here on the x and y axis, where x equals 0 and y equals 0. And then the graph here will kind of guide towards those asymptotes. So it's usually an easy way of like practicing when it comes to drawing it. All right, so what can we do with this parent function? Well, what can we always do with the parent function? We can transform it. So let's talk about transforming our reciprocal function. First of all, we have the parent function, which we just said was f of x equals 1 over x, which if we look at here, right, if I just change this 16 real quick to a 1, you're going to get, this is more of what the parent function looks like, right? You'll notice that the only difference between 1 and 16 is that the 16 kind of makes it a little bit wider. Okay, let's get rid of some of these extra scrap functions here. All right. So, transformations. So, if we have a function f of x and we are transforming it into g of x, the function is this. It's 1 over x minus h plus k. And you'll notice that h and k are, we've seen these letters before, right? H and k are the exact kind of shifts that we had when we did polynomials. They're the exact kind of shifts that we had when we did quadratics. It's always the same. So h is going to be our horizontal shift, right? And you'll notice that we put negative h, and the reason we put negative h is because if this is x plus 4, it's going to shift it to the left, right? It's the opposite of what you think every time on a horizontal shift. It's the same as before. If this is x plus 6, it's going to shift 6 to the left. If this is x minus 7, it's going to shift 7 to the right, right? So where k is the vertical shift. So our value here for k is going to be how much it moves up and down. And if we go back to Desmos, I can kind of show you how this works, right? So what I've done, I'm going to go ahead and get rid of this function here. And we're going to highlight this function here. Okay. So now we have this blue function. It's the same as the one before, but now I actually have these h and k toggles, right? Now, just for the sake of this, I'm going to actually make this negative h a positive h so that it moves the way we think it should, right? Because normally it'd be the opposite. So what we're going to do is first we're just going to do k, because k is very simple. If we make k, let's make k 5, what should happen? Well, we said before that k is the vertical shift, right? So as we move k up, the graph should move up. And watch what happens, right? Let's go up to 5. Well, what happened? Well, normally it wouldn't be able to cross the x-axis, right? But now if we look very closely, let's just for the sake of this, I'm going to put in the function y equals 5. And we're going to make this red because asymptotes are usually red. And you'll notice here, on the line y equals 5, that's our new asymptote, right? So as we move the graph up 5, the asymptote also moves up 5, right? Remember the asymptote before was on y equals 0. Now it's on y equals 5 because we've shifted it up 5, right? And now let's do the same thing for our h, right? If we make h 5, right? Or if this would be like h plus 5, we'll say, right? Which direction is it going to go? Well, remember that h is the opposite of the way you think it works, right? So if it's plus 5, it's actually going to shift it to the left, right? So if our equation was x equals 0 for the asymptote before, now it's going to be x equals negative 5. And voila, we have drawn our second asymptote. And now we can see everything we need for this graph. So not only have we transformed it, but now we can identify we can identify the asymptotes, right? We can identify our vertical shift. We can identify our horizontal shift. And the range and domain are also very easy to define now, right? Because we know the range of this function, in other words, our y values, it's going all the way up here. It's going to infinity, right? And then as it comes down, okay, well, the only thing y doesn't look like it's allowed to touch is this 5, right? Where y equals 5. So y touches everywhere but 5. So in this case, we would say the range is y such that y does not equal 5. And then when we look at our domain, right, the set of x values, well, from the negative side over here, we're good, we're good, we're good, we're good. Oh, it looks like we're stopping, right? Where are we stopping? Where x equals -5, where we put our asymptote, right? So the asymptotes guide us to our domain and range. So in this case, our domain is the set of x such that x does not equal -5. It's the only value it's not allowed to be. So it's all real numbers except for -5, right? Every number that exists. So let's go back to our notes here. And we'll see for our practice question, it says, state the domain and range and asymptotes of f of x equals 1 over x minus 3 plus 2. Well, first of all, before we even get into the domain and range and asymptotes, let's talk about what these numbers are doing, right? So we have our 2, right? So our 2 here is going to be our vertical shift, right? So what this is going to do is this is actually shifting it up by 2, right? So if our asymptote was normally on the line of x equals 0, right? And we shift it up to, or y equals 0, sorry. And we shift it up 2, well, what is our new asymptote going to be? It's not going to be where y equals 0. It's going to be where y equals 2, right? So we know automatically that one of our asymptotes is that y equals 2, because we shifted the whole graph up 2. And we'll go back and we'll graph this just to kind of show you that this is right? But our range, let's go ahead and do blue, that sounds cool. All right, so our range, right, is going to be this -3, right? Well, remember, what happens with -3? -3 actually shifts it to the right. So this should shift it to the right 3, right? Which means our range is going to be everything except for where y equals 3. So our other asymptote, or x equals 3, sorry. So our other asymptote is simply x equals 3, right? And now if we look at our domain and range, well, our domain is all of our x values except for 3, right? Because the asymptote shows where it's not. So we can say for our domain, we can say x such that x does not equal 3. And then for our range, we just know y can't equal 2. So that's fine. We can say y such that y does not equal 2. And now we've set our domain, we've set our range, we've set our asymptotes, we've done everything this problem's asking. So now we're gonna use Desmos, of course, to look at our work. Remember, this is 1 over x minus 3 plus 2. So 1 over x minus 3. So h, we're gonna make -3. Right? And then k, we're gonna make plus 2. Okay. And we said that the asymptote shouldn't be y equals 5, but it should actually be what? Y equals 2. And we said that our x should be at 3. Let's get there, 3. All right, now let's look at our graph. Well, it looks like we lined it up perfectly, right? So when we lined up k is 2 and h is -3 into our function, you notice that the asymptotes are at 2, 3. Our domain can touch everything except for where x equals 3. And our range can touch everything except for where y equals 2, right? This way. So everywhere except for where y equals 2. So that's it, right? That's our domain and our range. And that's lesson 4.1. That's it. So just to touch up on what we did, we start over here, right? We talked about inverse variation. We talked about direct variation for direct variation, as x gets bigger, y gets bigger at the same scale, right? And then for inverse variation, as x gets bigger, y gets smaller. So in inverse variation, it's the opposite. And then I showed you a couple of problems on how to do this using the formula here. We then talked about what a reciprocal function even is, with the parent function y equals 1 over x. We talked about how asymptotes are the lines that the graph can approach but never cross, and then how to find the domain and range. And then we went into what a transformation is, how h and k are the same they've kind of always been, and how we can use h and k to find our asymptotes, which basically make our domain and range very easy to find. All right, so that's it for 4.1. If you have any questions, let me know, and I will see you in 4.2.